Hello, everyone. Mr. Sutherland here, and we're going to continue our discussion about limits, really the building block of calculus. And so today, what we're going to focus on is evaluating limits by looking at tables. Um, so for the first few, I've given you tables, and we're going to predict what the limits would be. And these predictions are based on the accuracy of the tables we're given. Um, and then I'm going to have you make tables to evaluate the limits of some piecewise functions and some functions that are a little non-traditional, so you can see how you start to evaluate functions and even think about an algebraic approach to these and the link to continuity. So let's look at this first one. We're going to use the table to predict the limits. So for f of x, here are our values of the table. So when I am approaching positive 1 from the left, that means I'm approaching values, approaching 1 from values that are smaller than 1. So that means I'm really starting here and looking at what's happening as these values are getting closer and closer to 1. And we can see, I start in the negatives, I get to 0, then 0.5, 0.9, 0.99, and these values look like they're getting closer and closer. They're getting smaller there, and looks like they are approaching 2. Now, if I want to evaluate the limit as x approaches 1 from the right, well, that means I'm looking from the right, I'm looking at values that are larger than 1. My inputs are larger than 1, so I'm starting at 4, but I'm heading backwards, heading towards 1, and it looks like these values are getting smaller and smaller and smaller, and also headed towards 2. And then what that tells us, based on what we learned last time, is that if the left and right hand limit match up, we can say that indeed this limit would be 2. Now, a question's not here, but let's add it in. If I asked you what is f of 1, and we could see from the table there that given the values, there's no, you don't have to think about it much, f of 1 is 2. So these match, and when that match, that tells us that this table is going with a function that is continuous at x equals 2 because we're getting these two things to match. So let's take a look at the second table. So now we're looking at approaching -2. So again, from the left means we're going to approach from smaller values. So I start at -3 and I get closer and closer to -2. Now notice, -23, -12, -8, -6, -5.11, -5.011, but -2 is 6. Well, really though, the graph looks like, if I were to plot these points, it looks like as x is getting closer to -2 from the left, my y values are actually getting closer to -5. Now let's look at from the right. Now from the right means values that are larger. So I'm starting at -1 and heading back towards -2. So I'm at 3, 4.255, 5.61, 5.96, 5.996. So these values do look like they're getting closer to 6. Well then, what that means then is that the limit as x approaches -2 does not exist. Because remember, a limit to exist, the left and right hand limit has to match. And if I asked you, what is g of -2? From the table, we can see it's 6. So if we think about some sort of discontinuity, this is a jump discontinuity, right? I have a branch that's ending at like -5, and then I have a branch that's at 6. So there's some kind of jump going on there that makes it so it's not continuous. Our third example. So let's look at h of x as x approaches 3. So as I start to the left of 3 and get closer and closer, notice now my values just keep dropping. It doesn't look like I'm approaching anything. It looks like these values are getting smaller and smaller and smaller. So I'm going to say that that's -infinity. Now, there is an argument that you could write D and E here. I believe on delta math, both are accepted. Because the limit doesn't really exist. It doesn't go towards a single value. So both of these, like if this were a multiple choice question, both of these were not being answered choices. You would have one or the other. Now let's look at 3 from the right. So I start at 3.25 and I get closer and closer to 3. And notice these values are getting larger and larger and larger. So this is going to positive infinity. Again, I would be okay for that if you write does not exist. I think for one-sided limits, I like to use the negative infinity because it tells you kind of what the graph would look like if you were asked to sketch. And then at 3, we know the limit then does not exist. And from our table, we can see that h of 3 is undefined. So this is a case where we can think about what's going on. As I'm approaching 3 from the left, it's going to negative infinity. 3 from the right is going to positive infinity. So this is where it looks like we probably have a vertical asymptote at x equals 3, and that's why this is not continuous. Again, this is information we can get straight from the table. Now, let's start looking at evaluating limits algebraically by first looking at a table of values. So in 2a, I've given you this piecewise function, and I want to evaluate the limit as x approaches 2, what f of 2, and we'll talk about continuity. So the first thing I'd like you to do is let's fill in the table. So obviously this is something for the next few examples you may need a calculator for. So when I am looking at a piecewise function, remember this tells me which values of x I'm going to use the top function for, and then which values of x I'm going to use the bottom function for. So here, when x is less than 2, so like 1.9, I'm going to be plugging into the 3x minus 2, which comes out to be 3.7. Now, for 1.99, when I plug 1.99 in for x, I get 3.97. When I plug in 1.999, I get 3.997. Now, when I plug in 2, I'm going to be plugging into the bottom part because that is right here is where it includes 2. So if I plug 2 in for x, I get 4. If I plug in 2.001, we get 3.998. 2.01 into the bottom, and I get 3.98. And 2.1 into the bottom, and I get 3.8. So now let's evaluate limits. So as x approaches 2 from the left, it clearly looks like these values are getting closer and closer to 4. 2 from the right, it looks like they are also increasing and getting closer and closer to 4, so that we can definitely say, since those match, the limit is 4, and from our table, f of 2 is 4. Now, if those things are true, we can say it is continuous. And the justification that we use is we say it's continuous because the limit as f of x approaches 2 of f of x is equal to f of 2. If that statement happens, it is continuous. If this is not equals, it's not continuous. It's as simple as that. You'll explore next year in calculus a formal definition of continuity that this is the conclusion of. So if you get a good understanding of that this year and be able to justify that, it makes things next year a bit easier. All right, let's take a look at this next piecewise function. So for this one, we can have here when x is less than 3, I'm just going to plug into x plus 1. So that would be 3.9, 3.99, 3.999. Now, when x is 3, it says the value is 6. When x is greater than 3, we're going to plug into 2x minus 2. And so if you plug that into your calculator, you would get 4.002 for this one. For 3.01, 4.02. For 3.1, 4.2. All right, so now let's evaluate our limits. As I'm approaching 3 from the left, it looks like my y values are getting closer and closer to 4. As I approach 3 from the right, it also looks like my values are getting closer and closer to 4. So that means the limit does exist, and the limit is 4. But f of 3 is 6. So what does that tell us about the continuity of this function? It is not continuous. And it's not continuous because the limit as x approaches 3 of f of x does not equal f of 3. And let's think about what the graph must be looking like. Like I have a function here where I'm getting closer and closer to 4, but it doesn't reach it. Here we're getting closer and closer to 4, it doesn't reach it. But then at 3, the value is 6. So this would be an example of a removable discontinuity. There's a hole in the graph, and that's what's causing it not to be continuous. All right, let's take a look at the next one. Now, this isn't a piecewise function. Actually, there have been some similar to this on recent AP exams in the multiple choice questions where students are asked to evaluate the limit of this function. And it doesn't say to make a table, but a table is truly a good way to do this problem. We want to look at what happens as x gets closer and closer to 4. So if you plug in 3.9 into this, you will end up with negative 1. 3.99, you'll get negative 1. 3.999, you'll get positive 1. At 4, you'll get undefined. At 4.01001, you'll get 1. 4.01, you'll get 1. 4.1, you'll get 1. So as x approaches 4 from the left, it's always negative 1. So that's what my limit is. As x approaches 4 from the right, it's always positive 1. So that's what my limit is. Therefore, the limit does not exist, and f of 4 is what we would say undefined. So this is not continuous, and this one we can actually be a little different. It's not continuous because the limit as x approaches 4 of f of x does not exist. If the limit doesn't exist, this thing can't be continuous. And let's think about what the graph of this looks like. So I have that no matter what it looks like, when I'm getting closer to 4, my y value is negative 1. Greater than 4, my y value is positive 1. So this is a classic case of a jump discontinuity, right? Where you jump from one piece to another. All right, final question here. So I have a rational function. F of x is 5 over x minus 1 quantity squared. We're going to look at x equals 1 and evaluate the limit. So if I plug in 0.9, we end up with 500. 0.99, we end up with 50,000. 0.999, this is 5 million. And at 1, we are going to get undefined, if you were to plug that in your calculator. Now at 1.01, we have 5 million. Here we have 50,000. And here we have 500. So what's going on here? As I'm getting closer and closer to 1 from the left, those numbers are getting bigger and bigger. It doesn't look like it's getting closer to anything. So that's infinity. Or again, I think in Delta Math, they may have you even write it as does not exist. So if infinity doesn't work, try does not exist. 1 from the right, so going that way, getting closer and closer from the right, that's also going to infinity. Again, we could put does not exist. Now here's where you don't have an option. If they're both heading towards infinity, infinity doesn't equal infinity. They're not the same thing. So we say this limit does not exist. F of 1 is undefined, and this is not continuous because the limit as x approaches 1 of f of x does not exist. If you want to write the limit as x approaches 1, f of x does not equal f of 1, that would also work. So if we can think about what's happening here, from the left as we get closer to 1, the values shoot up. From the right as we get closer to 1, the values shoot up. So this is another case where you have that vertical asymptote. So we have lots of different examples here of how to evaluate limits using tables and connecting that idea of limit with continuity. I hope this is helpful. If you have any questions, please don't hesitate to email me. and I will talk to you guys later. Take care now.